All right, Honors Chem, we are going to learn our solubility rules for ionic compounds. Now, ionic compounds sometimes are called salts. So we normally think of salts as just sodium chloride, but anything that is an ionic compound is a salt. And so we are going to learn which ionic compounds or salts, different salts, are soluble in water and which ones are not today. Now we are going to use this solubility, and in solubility, we're going to basically say we're soluble in water. Okay, so water is what we're going to use for our solvent. And we're going to use these solubility rules to learn how to do net ionic equations for different salt reactions. All these salt reactions are going to be double displacement reactions. So let's get on with the rules here. So we're going to learn first what is soluble, meaning it can be dissolved in water, and then we're going to learn what's not soluble. So rule number 1, here we go. Rule number 1, ions, lithium, sodium, potassium, and ammonium. If we look at those ions on the periodic table, lithium, sodium, potassium, they're all in group 1. So our general rule is group 1 metals. Okay, so we're going to think of this rule as group 1 metals. So if I look at group 1 metals as well as the ammonium ion, they're always going to be soluble, no matter what. Okay, so if I have a salt made with any of those ions, I would expect it to dissolve in water pretty well. Okay, rule number 2. I have now the anions, the negative ion. Remember, positive ions are cations, negative ions are anions. So the anions, if I have acetate, nitrate, chlorate, or perchlorate, I would expect any salt made with those ions also to be soluble, no exceptions. Okay, rule number 3, chloride, bromide, and iodide. Notice chloride, iodide, and bromide are in our halogen. So we can loosely, not nearly as much with the first one, group 1 metals, but loosely we can kind of expand that to include all the halogens. But mostly chlorides, bromides, and iodides, they are all soluble with some exceptions. Now the exceptions for chlorides, bromides, and iodides are silver, mercury +1, and mercury or lead 2, and I would also say lead +4. So if I have silver, mercury, or lead bound to chloride, bromide, or iodide, I would not expect that salt to be dissolvable. I would expect that to be a solid in the bottom. It wouldn't dissolve. Okay, next rule, sulfates. Sulfates by and large are soluble. We also have the same exceptions. We have mercury and silver and lead, but we have some more exceptions. So our exceptions here are calcium, strontium, and barium. So not only would silver, mercury, and lead sulfate not work to dissolve, calcium, strontium, and barium sulfate also shouldn't dissolve very well. Okay? Let's move on to our insoluble. Okay, so insolubles, carbonates, CO3s. Okay, carbonates are not soluble. They will precipitate out, except for group 1 metals and ammonium. Okay, so if I have anything except for the group 1 metals or ammonium bound to a carbonate, I'm going to expect it to be a solid and not dissolve in water. Okay? Number 6, phosphates. Same thing. I would expect all phosphates to be insoluble except for group 1 phosphates and ammonium. They're going to be solids. Okay? And it's a good thing that they are. All right, sulfides. Anything with a sulfur is going to be insoluble except for group 1 metals and ammonium ions. Sulfites, same thing. not soluble except for group 1 metals. Let's see, lithium, sodium, potassium, and ammonium. They're going to be insoluble. Chromates, insoluble except for group 1 metals again. Permanganates, also insoluble except for group 1 metals and ammonium. Hydroxides, now this is the interesting one. This is the exception to the rule here. Notice the exceptions are all group 1. Hydroxides are a little bit different. It is group 1 as well, but we have 3 exceptions to that group 1. We have calcium hydroxide, strontium hydroxide, and barium hydroxide that are relatively soluble. Okay? So let's look at our solubility rules and see how we use them. Okay, so here we go. I've got a beaker here, and it is full of lead nitrate, lead 2 nitrate. And now, because nitrates are soluble, those ions are going to break apart. And I'm going to have lead plus 2 ions floating around in there, and I'm going to have nitrate ions floating around in there. So when we put a salt into water and dissolve it, that salt no longer stays as a compound. It breaks into the ions. That's why when we have salts and things dissolved in water, it can conduct electricity because it has ions in there. Okay? And if I have sodium iodide, I will also expect that to be soluble because sodium is a group 1 metal. Iodide is a halogen. Those are going to be soluble. Okay? They're going to break apart into the little ions. Now, if I put them together, let's see. That gives me new possibilities. I can do a double displacement or a double replacement. So nitrates and the leads, nitrates are all soluble, right? So if I have the nitrate now being able to access the sodium, sodiums are all soluble, group 1 metals. Nitrates are all soluble, so we would expect that to be dissolvable or soluble. But lead is one of our exceptions to the halogens. Remember, chloride, bromides, and iodides are all soluble except for silver, mercury, or lead. Okay? So the way we would write this out, okay, we would have the lead 2 nitrate. Let's do our molecular equation first. Lead 2 nitrate reacting with silver iodide, and we're going to do a double replacement reaction. So remember, double replacement or double displacement, the positive gets together with the other negative, and the second positive gets together with the first negative. So this lead is a plus 2, and iodide is a negative 1. So I'm going to need 2 iodides to balance out that charge, right? Sodium right here is a plus 1, and nitrate is a negative 1, so I'm going to need 1 of each to balance that out. Okay, so there's our skeleton. Now the next thing we've got to do is balance this. So hopefully you realize that I need to double my sodium iodides, and I need to double my sodium nitrates. So there's my balance. The next thing to do is to use our solubility rules. We used our solubility rules here, where we predicted that the sodium nitrate would remain soluble. So that aqueous means dissolved in water. So that means that's soluble. But we said that the lead 2 iodide would actually precipitate. Remember, because on our rules, halogens, the iodides, the chlorides, and bromides precipitate if they're bound with silver, mercury, or lead. And this is definitely lead. So this would precipitate out. So this we would expect to be solid. Okay? We would expect that precipitate out. Okay, so notice here on our picture, we've got some some sodium hydroxide right here. So we've got copper chloride. We would expect copper hydroxide to precipitate out with our hydroxide rules, right? Hydroxides are insoluble except for group 1 and strontium, barium, and calcium. Copper's not any of those. So we would expect it to precipitate out. Notice we get this blue precipitate here. That's going to be solid. And then the sodium and the chlorides are going to be off in solution. Okay? So let's do another example here. So sodium chloride. Sodium, let's look at our periodic table. Sodium is a +1 and chloride is a -1. So we're going to put those together. So let's put in our charges here. So that will be a 1-to-1 relationship. And then silver. Silver is one of our exceptions. Silver was always a +1, right? So silver is a +1. And then the other thing that we are looking for is nitrate. And we've already done nitrate up here, NO3 -1. So silver is a +1, nitrate is a -1. So 1-to-1 relationship there. Okay, so we're going to start off with our skeleton. Now remember, when we are predicting these reactions, these are all going to be double replacement or double displacement, whichever way you want to talk about them. So that means the sodium is going to get together with the other negative, and the silver is going to get together with the chloride. Okay, so sodium is a +1, nitrate is a -1, so 1-to-1 ratio there. And then silver is a +1 and chloride is a -1, so a 1-to-1 ratio there. Okay, the next thing to do is to check our solubility rules. Now, when we check our solubility rules, sodium is a group 1 metal, soluble, no exceptions. So that is going to be aqueous. Would you agree? And then, we don't have any rules about silver, but we sure do have a rule about chloride. Now, if I go to my rule about chloride, right? Chlorides are all soluble except for silver, mercury, or lead. I have that bound to silver. So that means because it's bound to silver, it is going to precipitate out. It is not soluble. It's going to be a solid. Okay? So my ionic reaction, remember everything that is soluble is going to break apart into its individual ions in water. So this sodium chloride is definitely soluble, and this is soluble. I should have put those in, right? All nitrates are soluble for the silver nitrate, and all sodium metals or sodium ions, ionic compounds are soluble because they're group 1. Okay, so that means sodium is going to be dissolved in water as an ion, and chloride is going to be separated as an ion, and silver +1 is going to be separated as an ion, and the nitrate is going to be separated as an ion. Okay. Now on the other side, silver or sodium nitrate is soluble, so it is also going to separate out into its ions. But silver chloride is not. It actually is more attracted to itself than it is to water, so it will stay together and form a solid. Okay, now just like in math, if you have the same thing repeated on both sides of the equation, you can cancel it out, just like in math. So do we see any repeaters here? I do. Sodium ion repeats, right? That repeats. And my nitrate ion repeats, so I can get rid of that. So what's left is what we call our net ionic. Net means what really is creating that reaction. Now, when we write our net ionic reactions, we always like to start with the positives, just like when we write our compounds. So we're going to have the silver ion, and we're going to have the chloride ion that are left. Okay. This is going to let me write. Nope. Okay. So those are what's left. And then this is what's left. Silver chloride solid. Okay. So our net ionic reaction is going to be silver chloride precipitating. Okay. Let's try another one. Potassium carbonate. So if I look up potassium is in our first column, so it's a +1, and carbonate is CO3 -2. So we've got potassium and CO3 -2. The calcium is in our second column, right here. So it is a +2. And bromine is right here, so it's a -1. Okay, so we're going to have, let's start another color. Let's just go down the list. So potassium +1, carbonate -2, calcium +2, and bromine -1. Okay, so now we need to figure out our relationships. Okay, so to balance out potassium carbonate, I'm going to need 2 potassiums and 1 carbonate. Now, is that soluble? What's our rule about group 1 metals? They're soluble, no exceptions, right? So that will be aqueous, that will be soluble. And then calcium bromide. So I'm going to need 1 calcium, 2 bromides. Now, is that soluble? We do have a rule about our bromides. Bromides are soluble except for silver, mercury, or lead. Calcium's not silver, mercury, or lead, so that will be soluble. Okay, double displacement here. So potassium is going to get together with the bromine. +1 plus -1. I'm just going to need 1 of each. Is that going to be soluble? Yep. Potassium's group 1, so that will be soluble, no exceptions. Why did that jump around? Let's rewrite that. Potassium bromide, and we're going to need that to be aqueous. And then calcium is going to get together with the carbonate. And that is going to be +2 plus a -2, so a 1-to-1 relationship there. Now, is that going to be soluble? We have a rule about carbonates, right? Carbonates are insoluble except for group 1, and calcium is a group 2. So that is not going to be soluble. So that's going to create a solid precipitate. Okay, so there's our skeleton. Let's go back through and balance it. Hopefully you realized as we were drawing this out, we need to put a 2 here. Okay, we good with that? All right, so our ionic equation, anything that is aqueous, we are going to break apart into the individual ions. Anything that is solid, we're going to keep together. Okay, so potassium carbonate. that is aqueous. So we're going to break it into the individual ions. So that 2 actually comes out because the potassium is a +1. We got 2 potassium +1 ions. We've got a carbonate -2 ion. We've got a calcium +2 ion. And we've got 2 bromide -1 ions. Okay? Now, the potassium bromide is also aqueous, so it's going to break apart into its ions. So we're going to have 2 potassium ions, and we're going to have 2 bromide -1 ions. And yes, you do need to put the charges on these ions when you write them down. But the calcium carbonate is solid. It's a precipitate, so we're going to write it together. Okay, now do we see some repeaters that we can get rid of? Hopefully you see some repeaters. So these repeaters, I have the 2 potassiums that I can get rid of, and I've got the 2 bromides that I can get rid of. Okay, so what's left is our calcium, our carbonate, and our calcium carbonate. Now we're going to draw the net ionic equation. We're going to write it with the positive ion first. So calcium is our positive ion. Calcium getting together with carbonate is going to make calcium carbonate solid. Now notice on my +2 and my -2, I put the plus after the 2 and I put the negative before the 2. It really doesn't matter whether you put the plus before the charge or after the charge, just as long as you put the type, positive or negative, and the magnitude of the charge there somewhere. Okay? All right, let's do our next one. We've got copper 2 sulfate and barium nitrate. So that 2 tells us a little bit about that copper, doesn't it? It tells us that the copper is positively 2 charged. So we have copper +2, and sulfate, the sulfate ion, if you remember, is SO4 -2. So that's going to get together on a 1-to-1 relationship. So copper 2 sulfate. Now, what's our rule? Look at the sulfate rule. Sulfates are soluble except for silver, mercury, lead, calcium, strontium, or barium. Copper is not any of those. So we would expect it to be aqueous. Okay? And then barium. Barium is a +2. And nitrate. Nitrate is a -1. So we're going to need 1 barium and 2 nitrates. Now, solubility. We do have a nitrate rule. Nitrates are soluble, no exceptions. So we are going to expect that to be aqueous. Okay, double displacement. So copper is going to get together with a nitrate. Copper is a +2, nitrate's a -1. So I'm going to need 2 nitrates here to balance out that charge. Okay? And then barium's going to get together with a sulfate. Barium's +2, sulfate's a -2, so I'm going to need 1 of each. Now let's decide whether these are soluble. Copper nitrate. Nitrates are soluble, no exceptions. That's the nitrate rule. Okay, sulfate. We do have a sulfate rule. They're soluble except for silver, mercury, or lead, calcium, strontium, or barium. Barium is an exception. So this is going to become a solid. Okay, we would expect that to precipitate out. All right, for our ionic equation, everything that's aqueous is going to dissolve and break apart into its ions. Everything that is solid is going to stay together. Okay, so anything that is aqueous, I want to change my color. Let me change my color. Okay, I'm going to draw So copper 2 sulfate. Copper plus 2. So copper plus 2 is going to be an ion. The sulfate, negative 2, is going to be an ion. The barium plus 2 is going to be an ion. And the 2 nitrates are also going to be ions. And on the other side, we've got copper plus 2 is going to be an ion. What did that just do? Okay, hopefully this will let me open this up again. All right, this is really maddening that my computer is doing this.